Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we continue our discussion about vectors for a trigonometry or pre-calculus course, doesn't matter which. You should have seen already my video on a geometric approach to vectors. If you didn't, and you don't know what a vector is, I highly recommend you go back and view that. In this video, we'll go ahead and just start with the algebraic approach of vectors. And we're not going to do a lot of arithmetic here. Instead, we're just going to focus on what a vector is algebraically, how to graph one algebraically, and the size of a vector, again, algebraically. Starting with the definition of vector notation, which I've already used, but let's just go ahead and stick with it. An n-dimensional vector where n is greater than 1 with name v is written with that v with a arrow on top. When I write it by hand, not using a typeset, I use a half arrow on top. Most people do. But if you want to do a full arrow, you can. That's totally fine. If x sub I denotes the signed distance between the ith coordinate of the tail and the ith coordinate of the head, then the coordinate form of the vector v is written as follows. Vector v is equal to x1, comma x2, comma blah, blah, blah. So what do I mean about the signed distance? Well, distance technically is always supposed to be positive. However, when I say signed distance, that means we allow for the distance to be considered negative. So let's see this in an example so that it makes sense. Express the vector with the initial point at 1/2, 3/4 and terminal point at -5, 5. Express that in component form. Well, 1/2, 3/4. I'm going to just showcase this on a number line here. Let's pretend that's 1/2 and this is a 3/4. So 1/2, 3/4. This is a point in space, not a vector. It's a point in space. And then that's the initial point of our vector. Our terminal point is going to be back 1, 2, 3, and up 5. We'll just pretend that's right here. Okay. So -3, 5. That's the point Q. This is the point P. And we want to know what is the vector going from point P to point Q. What is the notation we'd use? All that fun stuff, right? I do know the initial point is point P and the terminal point is point Q. Well, by definition, the ith coordinate, let's just talk about the first coordinate. The first coordinate, x sub 1, denotes the signed distance between the first coordinate of the tail and the first coordinate of the head. So it'll be -3 minus 1/2. That's what the first coordinate of this vector, which I'll call v here, v is equal to, notice it's not a parenthesis, nor is it a bracket. It's like a sideways v, or a v bracket if you want to call it that. The first coordinate is going to be -3 minus 1/2. So where it ends minus where it begins. And then the second coordinate, you'll again take where it ends minus where it began. So 5 minus 3/4. And sorry if you can hear a lot of sound. It is a major storm outside right now. All right. So simplifying this vector down, that's a negative, 6/2 minus 1/2, -7/2. And then 5, which is 20/4, minus 3/4 is 17/4. So this vector is -7/2, positive 17/4. Those are the components of that vector. So, and notice again, we use a little bracket notation right there. It's essentially a guide. How do I get from beginning to end? To get from this beginning to this end, I would go back along in the x direction, 3.5 steps. So basically a half plus 1, 2, and a 3, and then up 17/4 steps. We'll just say that that's what that is, right? So you've been dealing with this your entire math career, rise over run, all that fun stuff. But that's what's happening here. Just a guideline to get from point P to point Q. Notice that there are an infinite number of vectors in the plane represented by that vector. I could have another one over here if I wanted to that would have the same vector coordinates. In other words, this is vector v because it equals -7/2, 17/4. It goes back 7/2 units and up 17/4 units. So because of that ambiguity, we would like to have a better way to talk about vectors to where we could say, no, when I say -7/2, 17/4, I really mean this one vector. And we'll get to that in a moment, but right now, we're just being asked to sketch a couple vectors. These vectors we're going to use throughout this lecture series. So vector v is -3, 1. So I'll just put the initial point here. I'll go back 1, 2, 3, and up 1. So this vector, which let's see if I can, yep, there we go. That's vector v. And vector u is 5, 5. Let's just plot a point there. We'll go over 1, 2, 3, 4, 5, and up 1, 2, 3, 4, and 5. And again, connect those points right there. And that's vector u. Again, because I'm just drawing this in space, and there's no real coordinate system that I've plotted here, there are an infinite number of representations for the vector v. I could plot another vector v right here by saying, oh, that's back 3 and up 1 or whatever. So I could do this all day long. And that brings us to the definition of standard position. A vector with an initial point at the origin is said to be in standard position. And this allows us to concretely lock down a vector. So I could say, no, don't graph the vector u, which is 5, 5. Don't graph that just anywhere. I want that graphed in standard position. There's only one vector that matches vector u that's graphed in standard position. That vector is 5, 5. So here's that question. Let's go ahead and put in a Cartesian coordinate system here, just real quickly. I'm not going to be super accurate with measuring at least, but I'll keep that off to the side so that I can draw it. The vector v in standard position starts at the origin, it goes back 1, 2, 3 steps and up 1 step. So it terminates there. I'll just go ahead and use this bad boy right here to draw it. So something like this. Oops. There we go. That's the vector v in standard position. There's only one vector v in standard position. So that's a good way of doing that. And I happen to know that this is going to be 45 degrees, but if I'm freehanding this, it might not be. So let's go ahead and freehand the vector u, which is 5, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5. So let's see if I can somehow line that up perfectly. Let's see, I want to cross paths here. That's my target. So let's go ahead and target that. There we go. Good enough for me. I'm going to draw it in red. Okay, there's my vector u. Again, u is the vector 5, 5. I just drew those cross hatches in there for guidelines. That's all. So, and again, there's only one vector u in standard position. Let's see, we also talked about in the previous video, which was a geometric exploration of vectors, we talked about the magnitude or size of a vector. Now let's talk about that algebraically. The magnitude of a vector v with coordinates a, b is denoted with an absolute value. And that is going to be a common theme throughout all of the rest of mathematics. When you talk about the size of something, the size of something is denoted with these absolute value signs. So the size of v is going to be the square root of the sum of the squares of its components. And by the way, that extends if you have a vector in 3 dimensions or 4 or 5. Again, it's the sum of the squares of its components. Now in 2 dimensions, the proof of this magnitude is very, very easy. If we all agree that the size of a vector does not change no matter where you place it, then let's go ahead and place this vector in standard position. And so doing that, let me go ahead and grab this, and I'll do a geometric proof here. Where is this? There we go. And let's just pretend, just keep it simple. We'll put this vector in quadrant 1 from standard position. So let's just say that this vector is vector v, right there. And remember, vector v has coordinates, or has, its component form for vector v is equal to a comma b. Well, that means you've gone over a units and gone up b units to get to this head of this vector. Over a and up b. Well, if you take a look at this, this is a right triangle. And so the length of this hypotenuse would be the square root of a squared plus b squared. That is, the length of v, which is defined to be the magnitude of v, is square root of a squared plus b squared. And then you're done. QED. Proof is over. Very fast proof, very nice proof. So let's quickly compute the magnitudes of those 2 vectors we've been using. The magnitude of vector v, by definition, or by the theorem actually, is the square root of -3 squared plus 1 squared, or in other words, the square root of 10. That's the length of that vector v, no matter where you place it. And the length of vector u, or the magnitude of vector u, is going to be square root of 25 plus 25, which is 5 root 2. And that should make sense because you have a horizontal side of length 5, a vertical side of length 5, so your hypotenuse, because it's a 45, 45, 90, must be 5 root 2. All right, so that's all I want to do in this video for the algebra or algebraic approach to vectors. In the next video, we'll actually start doing algebraic addition of vectors and go through some properties of vectors. And then we'll eventually get into applications of vectors, which is incredibly important.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much, that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.